Behind almost every single piece of technology you touch every day, there's this hidden engine, an invisible architecture that actually makes our digital world possible. So today, we're going to pop the hood and take a look inside.
So let's start with a question. Think about it for a second. Your social media feed, the GPS that gets you across town, the password that keeps your email safe. I mean, on the surface, they seem totally different, right? One's about friends, one's about roads, and one's about security.
But the wild thing is, they're not different at all. Deep down, they are all built on the exact same powerful foundation. And that foundation is discrete mathematics. Now, this is probably not the math you remember from high school. It's something way, way more essential to how we live now. So what on earth does discrete even mean? Well, think of it this way. If you remember calculus, that's the math of smooth, flowing, continuous change, like the perfect, graceful arc of a ball flying through the air. Discrete math, that's the math of separate, individual, countable things. It's not the arc of the ball, it's the distinct number of steps you have to take to run and catch it. One step, then another, then another. See, computers don't think in smooth curves. They think in steps, on or off, 0 or 1. And that is why this is the true math of the digital world.
You could even say it's the mathematical toolkit for building the digital world. It's like if you want to build a skyscraper, you need to understand physics. Well, if you want to build a social network or a search engine, you absolutely need this toolkit.
So, how does this toolkit actually work? Where do we even start? Well, it all begins at the most basic level imaginable, taking all the messy, chaotic information out there and giving it some structure, giving it rules. The very first tool we pull out of the box is the idea of a set. Now, that sounds fancy, but it's just a collection of distinct objects. That's it. A really great way to think about it is your favorite music playlist. Each song is a unique, distinct item, and the playlist itself is the set that holds them all. Simple, right? But this is how computers start to group things, from your list of contacts to all the files in a folder.
Okay, but just grouping stuff into piles isn't enough. We need a way to reason about it. And that's where logic comes in. If sets are the words, the nouns, then logic is the grammar. It's this rock-solid formal system of rules that lets a computer figure out what must be true based on what it already knows. There's no guesswork.
For example, if you know for a fact that every single file in a folder is from 2024, and you also know that a specific file is in that folder, well, logic guarantees that the file has to be from 2024. It's a certainty. Every single if-then statement in every piece of software is just a tiny version of this logical machine at work.
So, we've got our information organized into sets, and we have the rules of logic to reason about it. What's next? Well, the next step is to understand the relationships between all those different pieces of information. It's time to connect the dots. And what's really cool is that this whole field started with a famous brain teaser back in the 1700s. The people in the city of Königsberg had this puzzle. Could you go for a walk that crosses every one of their 7 bridges, but only cross each bridge exactly once? The brilliant mathematician Leonhard Euler cracked it. And he did it by realizing that the shape of the land, the length of the bridges, none of that mattered. All that mattered were the landmasses, which he just drew as dots, and the bridges connecting them, which he drew as lines. And by boiling the problem down to just dots and lines, he basically invented an entire new field of mathematics called graph theory.
And that incredibly simple idea, dots and lines, is literally the blueprint for our entire connected world today. Think about it. In a social network, people are the dots and friendships are the lines. The internet, web pages are dots and hyperlinks are the lines connecting them. Your GPS, intersections are the dots and the roads are the lines. It's the exact same fundamental structure, scaling all the way up from an old-timey puzzle to the whole global internet.
Okay, so we've got our data organized. We've mapped all its connections. Now for the final and maybe the most crucial piece. What do we actually do with it? How do we put it to work? This is where we find the engine itself.
That engine is the algorithm. And an algorithm is really nothing more than a recipe. It's a precise, step-by-step set of instructions that tells a computer exactly what to do to solve a problem. That's it. From sorting your emails to recommending what movie you should watch next, it's all just a computer following a recipe.
But here's the multi-trillion-dollar question that pretty much all of modern computing depends on. If you want to bake a cake, does it matter which recipe you pick? Of course it does. Some are way better than others. And for computers, the difference isn't just a little bit better, it's absolutely staggering.
I mean, just look at this. Let's say we're sorting 10,000 photos. A smart algorithm, a good recipe.
can get it done in less than a second. A clunky, brute force algorithm, it could take several minutes. And that's the difference between an app you love to use and one you immediately delete.
But here's the really crucial part. That gap in performance, it doesn't just grow, it explodes. It becomes astronomical as the problem gets bigger. And this core idea is called algorithmic complexity. It's how we analyze the efficiency of our recipes.
Let's make this super concrete. Say you have a slow algorithm. To sort just 10 little items, maybe it takes about 100 steps, or operations. Totally fine, right? No big deal. But now, watch what happens if we jump up to 1,000 items. So 100 times more stuff. You might think the work would be 100 times more, but it's not. With this slow recipe, the number of operations jumps by 10,000 times, all the way to 1,000,000.
And if we go all the way up to 1,000,000 items, get this, we're now at 1,000,000,000,000 operations. The numbers just become insane. And that is why understanding algorithmic complexity is so important. It literally defines the boundary between what's possible for our computers to do and what will forever be impossible.
So, let's pull all these pieces back together. What is this unseen engine, this code of our world, that's running everything?
It's actually this beautiful, elegant, logical structure. We start by using sets to bring order to raw information. Then we apply logic to reason about that information perfectly. We use graphs to map out all the complex connections between the data. And finally, we use efficient algorithms to process it all at incredible speeds. Those are the 4 pillars holding up our entire digital age.
This is the invisible language being spoken right now by the device in your hand and by every server humming away in a data center across the globe. It's already built the world we live in. The only real question left is, now that we know the code, what are we going to build with it next?